Welcome back to Mechanisms and Simple Machines. Quick recap from the last video. Ideal mechanical advantage, distance effort over distance resistance. So if you ever got two distances, you can divide those two and calculate the IMA. AMA is force resistance over force effort. So if you ever are given two forces, go ahead and divide that resistance by that effort and you've got a mechanical advantage, but actually you've got the actual mechanical advantage. So now let's look at some simple machines of a lever. Lever just being a rigid bar, weight on one side, resistance on another, or don't have to be on the sides, they can both be kind of different places, and you got the fulcrum that kind of moves around. First type of lever we've got is the first class lever. First class lever has that fulcrum that's located in the middle of our object itself. Then we have effort and resistance applied in the same direction, but causing this lever to go in different directions. Effort here is trying to go counterclockwise, resistance going clockwise. So when do you have mechanical advantage that is equal to 1? Well, mechanical advantage equal 1 when your IMA equals your AMA. Why? Because your forces divided by force would equal 1. Your distance divided by your distance would equal 1. So what happens when your mechanical advantage is less than 1? Well, mechanical advantage less than 1 would mean that your effort force has to be greater than your resistance force, or the distance to your effort is less than the distance to your resistance. Both of those give you a mechanical advantage less than 1. And then how do you get a mechanical advantage greater than 1? Where it takes less effort to overcome a larger resistance. Second class lever. Second class lever has a fulcrum at the end, a resistance between then the effort and the fulcrum. So what do we know about a second class lever? A second class lever has a mechanical advantage greater than 1. That's your wheelbarrow example. You've got 200 pounds of resistance in the middle. Takes you only 100 pounds of effort to be able to lift that up. So therefore you've got a mechanical advantage greater than 1. Third class lever. Third class lever has your fulcrum at the end, but your effort's in the middle, your resistance at the end. So again, that's our tweezer example. You're squeezing that middle there, and your resistance then being at the end, that's trying to resist what you are trying to do. So when you have that third class lever, what's being created? Well, you got a mechanical advantage that's less than 1. So it takes more effort and less resistance that you've got there. So your input is greater than what your output is for that third class lever. So when we're looking at levers, we're going to break it down. We're going to look at moments that happen at each one of those individual forces themselves. Moments are going to be used both first quarter and second quarter as we're trying to solve stuff, but we've got a moment. We've got a perpendicular distance to that force, and that goes and calculates a moment. There's a moment here, moment here. Moments are distance times force, or sometimes flowing off my tongue sounds better with force times the distance. So different terminology we've got to do is torque. Torque is also known as that moment, but it's a force that produces or tends to produce rotation or movement upon that object. So you got moment, or the torque that's being applied to that lever. So let's do some calculations. Calculate the effort moment. So effort is force times distance. So we've got distance times force. So therefore that effort moment is 82.5 inches pounds being applied. So 82.5, so much torque is being applied to that effort. Resistance, we didn't have enough to calculate with. But what do we got? We're looking at equilibrium. So let's say we want to set that teeter-totter equal. We want things in balance. We don't want things to move. We're going to go second quarter and look at trusses. We don't want those trusses or those bridges to move. We want equilibrium at those individual points. We don't want any rotation. So when we're talking no rotation, we're looking at then the sum of all the moments clockwise is equal to the sum of all the moments counterclockwise. So when we go back to this effort is trying to go counterclockwise, this resistance is trying to go clockwise. We want this moment here to equal that moment there, or the torque here equal to that torque that's being applied on that side. So we've already calculated this one on the previous slide. We know that the moment at the resistance is force times the distance. So force times that distance, divide both sides by that 36.66. We know that the distance to that resistance should be 2¼ inches if we want this lever to stay in equilibrium and stay flat and not rotate for us. So the lever ideal mechanical advantage. What did we say? If you've ever given two distances, divide the effort distance divided by the resistance distance, it will give you a mechanical advantage. So you've got ideal mechanical advantage. For my math folks out there, you've got this resistance is going to go and it's going to push that clockwise. Effort's trying to go counterclockwise. So really you're looking at distances being the circumference of that circle that's trying to being rotated there. But when you divide your circumferences, you got 2 pi times a radius, 2 times a radius of that circle. What do you got? You can cancel out those 2 pi's, so really you can go ahead and just divide those forces. So let's look at AMA. What did we say? When we got AMA, it's force over force. So if you have two forces, divide the two of them, you've got a mechanical advantage, and more importantly, you've got the actual mechanical advantage. So for this one, resistance, 32. Effort, 16. So if we take 32 divided by 16, that gives us a 2, 2, 1. What is the ideal mechanical advantage? The ideal mechanical advantage, we take 2.25 divided by 5.5. We get 5.5 divided by 2.25. And what do we get? Well, we get an ideal mechanical advantage of, so why do they go ahead and they put 2.44? Well, they go ahead and they do 2.44 because they use significant digits when they divided those two. We all know that that is half. So really the ideal mechanical advantage of the system is 2, 2, 1. The next type of simple machine we want to look at is wheels and axles. Wheels and axles are pretty much just a lever arm, but it's attached to that shaft itself. So you got the axle that's inside of there. So we're looking at pretty much the radius of the axle, and then we're looking at the radius of the tire or the wheel that's being acted there. So we've got a wheel, or the axle in our car. The axle drives that wheel. So you spin this, it spins that there. What's an example of a wheel driving the axle? Well, just another place in the car when you turn that steering wheel, and then when you try to turn on a hose. You spin that dial on the outside, you're spinning that axle on the inside that's releasing that pressure so your water can come out of your hose itself. So when we're talking about wheel and axle IMA is distance divided by distance. So if we're given two distances, we just divide them and then we calculate, like, oh, cool, we just have two distances, let's divide, we've got IMA. So effort, resistance. So we're looking at this question itself and we want to be able to make sure we put the right inputs in. What's the input? What's the output? So if the axle is driving the wheel, so our effort is the axle, we're spinning that axle. Our resistance, or our output, is the wheel itself. So by looking at that, we have got the effort being the axle, which is the input, is 6. We've got the wheel being the output is 20. So then what happens if the wheel is driving that axle? So we're inputting the wheel is the input, and the axle is what the output then that's working there. Well, then we do that inverse of that. We take 20 divided by 6, we get 3 1/3 to 1 ratio there. So this ratio here is less than 1, which means it takes more effort. The effort is larger than the resistance. Then here, what do we have? We have IMA, or mechanical advantage, greater than 1, so it takes less effort than resistance to be able to spin those two. Actual mechanical advantage is just forces. Doesn't matter what kind of simple machine you're looking at. If you were given two forces, divide those two, you've got a mechanical advantage. So we're looking at this one, the wheel. So the wheel here is driving the axle. So our input is 70, our output is 200. So our effort is 70, Our resistance is 200, so 200 over 70 gives us that 2.86. So what's the efficiency? Well, the efficiency is the AMA over the IMA. So we have an AMA of 2.86. From the previous slide, we had an IMA of 3.3 when the wheel was driving the axle. Divide those two, you've got an efficiency of 85.9%. Nothing can be more than 100% efficient. If you ever come up with something more than 100%, you let me know. I want to invest in the ground floor. So that was our levers on our wheel and axle. Next, we'll be going over pulleys.